hit the lucky number 13 students threshold. So I've had a few really good questions in office hours. Does anyone else have any questions from homework stuff? Yes, that homework that everybody is working on.
Jay, I have a question.
Go ahead.
So maybe the same thing, chapter 8.3. You guys were doing it earlier, 38.
I see the other questions in chat too, so don't worry. I'm going to come back to those. This guy?
Yes.
Okay. What about him?
So do you make a triangle, then you plug the body in, or is there any other way to do it? Like for example, like inverse of cosine of 1 minus x, that means like hypotenuse is 1, right?
Yes, because it's a ratio. You can make it over 1, so everything's a ratio. Yeah.
Then one side of the leg is 1 minus x.
Yes.
Then you just use the Pythagorean theorem to get the other side of the leg.
Yes. And then you can figure out sine. Yeah, exactly. It's not any different than what we did already.
Yeah,
Yep.
just making sure. Thank you.
Oh, yeah. Now, you did have an intriguing part of that question you asked. So we did stuff like this. Sine of inverse cosine of 2/7, right?
Yeah.
Draw a triangle. This is an angle. This would be 2, this would be 7. Use Pythagorean theorem to figure that out. So that'd be square root of 45, I think.
Okay.
Right? All right. Now, so then sine would be square root of 45 over 7. Is that cool?
Yeah.
Another way to do this is, this says that cosine of theta is 2/7. Sine squared theta plus cosine squared theta equals 1. You can throw that in there and sine. But do you understand the math is the same? We're just doing it in different order.
Yeah.
We did Pythagorean theorem here. We just didn't do it on 2/7. We did it on the parts of 2/7. I mean, so these are actually the same method, just differently organized. All right.
Which way should I get used to? Like either like prefer? No.
I mean, it's really nice to know. You should know how to set up the triangle based on the inverse, because there's broader applications of that. But there's good stuff to get from, I mean, trig identities, but we're going to get a lot of practice with trig identities soon anyway. So I sort of would lean in this first method.
Okay.
But to be honest, both methods are fine.
Okay. Thank you.
So let me see. I got to catch up with chat here. Let's see. So two people private messaged me. 9136 and 39. Okay. Oh yeah, that looks yummy. So one thing this requires you to know, and this is something I was talking about in, did I do this yet? Yeah, I did. Okay, recording's going. All right. Can you remind me what even symmetry is and what odd symmetry is? Anybody remember?
Yes. Isn't it like for even you strict the parabola or whatever it was?
Yeah. Even, the easiest way to remember even is y equals x squared, even power, right? Even power, even symmetry. So odd symmetry, the easiest way to remember it is cubed. Odd power, odd symmetry. So here, when I plug in x versus when I plug in negative x, how do the outputs relate? Are they different? Like 2 versus negative 2. When I square them, do I get different outputs?
Same.
Same outputs. There. That's even symmetry. Odd symmetry is when I plug in, say I plug 2 in and plug negative 2 in for a cube. How do the outputs relate?
Different.
In what way?
Plus minus.
Yeah, one is the negative of the other. I like it. So that is the basic definition of anything with odd symmetry. But it's really good to know the visual. This is symmetric through the y-axis. This is symmetric through the origin. So look at cosine. Right? Which of course looks like an octopus, but we'll get past that. So here's cosine. I kind of put it in the right place, but what kind of symmetry does it look like it has? Pretending like I drew this correctly.
Even.
Yeah, this is evenly symmetric, meaning that cosine of negative x equals cosine of x. And of course, sine has the opposite symmetry. In fact, right in the middle, it sort of looks like a cubic, doesn't it? Sure. You see that right in the middle? So that's going to have odd symmetry. So sine of negative x equals sine, Jeff, negative sine of x. So that will help you out with some of this stuff in here. What do you think secant does? Which kind of symmetry do you think secant has? Which trig function is secant related to directly?
Cosine.
Yeah, so secant has the same symmetry as cosine. So they're both even. That's one little thing that's going to help you with some of these, right? And a life pro tip is to put yourself in an uncomfortable position when you're in class. That'll help you stay alert. But your specific question was on 36. What do you have? I know this looks like there's a lot going on. One thing is they slipped this in. What the hell? This is too early. So that's the big thing. Okay. So I'm noticing this. We haven't even talked about double angle formula yet. So I don't know what that's doing in there. Hold on. Really don't think. So one thing is this whole thing, which you got to know anyway, because there's a whole other section that deals with symmetry. But we haven't talked about how to deal with double angles yet. So it's a little bit disturbing they put that in here. Let me check here. I'm going to clear all this away. You ready? Okay. I'm curious. I'm pretty sure we did not talk about double angles. No. Here's the even and odd stuff. Yeah, we definitely did not talk about double angles. So who asked that question? So obviously this problem is not doable. I never realized that. Nobody ever brought that up before. We don't know the double angle formula yet. So there is a formula that's coming up that's specifically called double angle formula. So we can figure out what sine of twice any angle is and cosine of twice any angle. But 36, you actually currently cannot do. Once I tell you one thing. No, I'm not going to do it. Don't worry. So yeah, if on your homework you want to put next to 36, can't do, or if you want to look up the double angle formula and do it, that'll work too. Either way. Let me see. Let me look at chat again. 39 is the same thing. No, 39 is a beautiful problem. I love 39. I would. Now stay with me, guys. I really want you guys with me on this. All right. I love the shit out of 39. And there are so many trig identity problems that are related to a process you can use in number 39. Now watch, you ready? First thing I want to take care of. What's the most immediate thing we can take care of that we just talked about a minute ago?
All the function.
What sign of negative x?
Sine of x.
So again, sine looks like this. So what's sine of pi over 2 and sine of negative pi over 2? Are they the same value?
No.
Nope. One is the negative of the other one. So it's, I can rewrite the bottom of this as 1 minus sine x. Is everybody with me? Sine and negative x. This piece equals negative sine x. Okay. All right. Stay with me. Stay with me. Oh, man. I love this shit so much. And it always makes me a little sad that I am very often the only person that feels that way. But just stay with me. Let's see if anybody agrees with me. The reason I love this frickin' problem is because of this. Watch. So this says verify this identity, which basically means it's true. I just have to show that it's true. So I can pick one side or the other to work with. Now, does it look like there's much of a damn thing I could do? Well, here's the thing. If this is true and I work with this side, what has to end up being on the top? If this equation is true and I work with this side, what do I have to eventually get on the top?
1 plus sine of x.
All right, you ready? This is not something to do every time, but there's something here that really helps. So watch what I'm going to do. I'm just going to frickin' multiply top and bottom by 1 plus sine x, because then I've got something there that's supposed to be there. This is not exactly a last resort kind of thing, but it's not always a first resort kind of thing. But I kind of love this shit. All right. So let's look at the bottom though. Why does this feel like it might be the right thing? What does it feel like this is related to? Does anyone remember? Shit. That's what I get when I don't have any teeth. How do I do this problem? How do I simplify this? What do I multiply by? Top and bottom. Anybody remember? Does anyone remember this course?
Yeah, that's it. I don't remember what it called. Like I
don't care
remember
what it's called.
difference of
Don't worry about what it's called. Tell me what you would multiply by.
rad 7 plus 1.
Yes. Anybody remember what it's called? What it's called is secondarily important. It's not prime. The primary importance is what do you do? The secondary importance is what do you call what you just did? Does anyone remember what that's called?
Is it
Reciprocal.
Conjunction. Oh, conjugate.
Conjugate. Doesn't this look like the idea of a conjugate? Do we have identities relating 1 in sine squared? So when I multiply this shit out, isn't it going to be related to an identity?
Cosine squared.
Don't go too far. That's as much as I'm going to do. That's it. You got to finish it out. But so there are two things there. It's kind of like, I know there's supposed to be 1 plus sine x up here. So what do? I just put 1 up there. And to make it legal, I put 1 down there too. And then I have faith that it's going to work because I know the equality is true. I know it's got to work somehow. I could have done it the other way around. I could have put a 1 minus sine x up here and a 1 minus sine x down there, blah, 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 because there's supposed to be a 1 minus sine x down here, right? But Now you have the idea of maybe it's, if there's a fraction, I can multiply by the conjugate. It's not really a conjugate, but the same kind of idea. Maybe? Does anyone remember? So, all right, we got sine squared plus cosine squared is 1. Give me another Pythagorean identity.
1 plus tangent squared of x equals secant squared.
11. So if I saw on the bottom of something I'm supposed to be, what do you call it? You can do it, Jeff. Proving secant x minus 1, and I multiply by secant x plus 1 on the top and bottom, it's going to make sense because it's going to become secant squared minus 1, which is that identity. Do you see that? Can you see that? Can you see it? Okay, maybe. I feel like, anyway, I'm sorry. I'm remembering a certain scene from South Park. Do you see? No, but okay. Something that's going to help a lot is after tonight's lecture, I'm going to feel a little more comfortable. I'm going to go ahead and unlock the complete list of all the identities. And you can have that bad boy sitting next to you as you do homework. At the moment, you should have all the ones we've talked about so far frickin' put together for yourself, sitting next to you already. Right? If you don't, I don't understand you. Okay. Now, eventually, hopefully, as you use them, they get in your head so that you can take a test or a quiz legally without having all that stuff written down. All right. Let me see. Did I miss anything? I'm gonna stop sharing. Is that all right? You guys ready? Let's see. What else did I miss here? Find equation of the graph. Oh, you mean stuff like oh, what was it? Yeah, like these problems. That person. Tangent. Okay. Let me see. Oh, these. No, tangent. So. Ooh, yeah, that looks yummy. Doesn't that look yummy? Whatever, Jeff. All right. I don't know if that's what I assigned. I can't remember. Probably assigned. Yeah. Oh well, it doesn't matter. What is? All right. All right. All right. Oh, 42. All right. So, guys, where does tangent normally live? I love asking that kind of question. Where does tangent normally live? Like the base tangent, it lives between what and what?
-1 to 1.
No. Oh, I see what you're talking about, but definitely not. No. That would be sine or cosine. I mean the inputs,
Negative pi over 2 to pi over 2.
because these are what set up the walls, right? So that's what I mean by lived with it. These are the walls it lives with it. And of course, it's unbounded in terms of range, right? That's at 1 and -1 at there, and then it goes. Okay, so how do we get from there to there? Well, what kind of shifts have happened? Has there been, I don't want to say this. Well, let's see here. 1, 2, 3, 4, 5. So that's the midpoint right there. Interesting. So at the midpoint, it's 0. At these points, it should be 1 and -1. It looks like that's exactly what it is here and here. I don't know. Are you guys following what I'm saying right now? So again, I've got the 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I've got those key points. And I can see it's doing what it's supposed to be doing at the 5 locations. Now, of course, the 5 locations, are they in the regular place? All right. So has the amplitude changed? How can you tell that on a tangent? I'm pretty sure I talked about this with tangent. I said at the time, tangent does not have an amplitude because it's not bounded. But if it was like 2 tangent, then of course, where should this happen and this happen?
At 2 and -2.
It would be at 2 and -2, right? And it looks like they're still at 1 and -1. So it's still tangent. There's no number. There's nothing here. There's just a 1 there. Is everybody with me? So tangent, amplitude makes no sense for tangent, but I can still consider the multiplier where an amplitude would normally sit. I know what it would do. It would affect where it is at these steps. So I can see if there's something there, and there's nothing there. There's just a 1 there. So what 2 things have happened to it along the X direction? There's 2 things that have happened to this poor dude.
Move it to right.
Yeah, definitely had a phase shift. And so now watch. If I undo the phase shift, are you guys now watch? This is kind of, if I undo the phase shift, wouldn't that just put it back to here? I really want, so this is, all right. I have not done a problem like this since last semester, to be completely honest. I didn't look at these because they're just, if I don't know how to do these, I should quit. Right? I mean, this is bread and butter for me. I'm a freaking math teacher. Ooh, so of course I should know how to do this shit. So what I'm showing you right now is the first thing I'm thinking about as I'm looking at this problem. And I like to deconstruct. So watch, if I put it back, if I take the phase shift away, how does it help me figure out what K is? So what's the normal period for tangent?
Pi.
And to figure out the new period, I would take pi divided by K. Is that cool? All right, so how do I figure out what K is? Well, I know what the new period is. What's the new period?
Pi over 2.
Pi over 2. So I need this to be pi over 2. So you can pretty much just look right at it and tell what K is. You know exactly what K is. I don't have to do any work. Can you see that? Pi over K equals pi over 2. Well, K is freaking 2 then. Shit. Are you guys? I'm doing too much of this problem. I've already done too much of this problem. So now all you got to do is figure out how much the phase shift is and if it is it negative or positive. And I'm going to leave that for you to do. But really the question is, what do I look at to get what I need for the equation, correct? That is your question. Because that's a good question, and that's the question to ask. And I just gave you some ideas of how to find what you need to figure out the parts of the equation you need to fill in. Is that all right? Does that help? Or is that enough? Or is that not enough? Okay, okay. I got to remember that. At some point, my Zoom updated, and now it does not tell me when I get a chat when I'm sharing the screen. That sucks. All right, so I'm going to stop sharing. Is everybody ready? You guys copy this down yet? That's what I would do if I were you. All right, it's going away. It's going away, it's gone. Okay. I think I'm caught up on questions, right? Yes. My jet turbine is calmed down. Good, okay. So, what I want to do tonight is I want to focus on 2 major players for identities. Also, did I say this during class time? There is a practice quiz up. Oh, and I haven't said this either. I said this during office hours. I'm going to change the quiz to be Wednesday. Does anyone have an objection to that? I have altered the due dates for 8-2 and 8-3. I think I pushed them back one day. So like 8-2 is due today, I think now. And 8-3 is due tomorrow. They got a little more time there. You always got more time. I mean, shit. I let you turn in stuff late, and I try to do as much as I can to make you do something before the quiz happens. But you know, I understand life happens. So let's do this. Let's get this down here. So if you go to Canvas right now, let me turn off my jet turbine. It's bothering me. I don't know. If you guys think I'm yelling at you, it's because I'm yelling over that. All right, let me reset my audio now real quick. Okay, does that sound better? Okay, guys, this is Jeff coming at you. All right, so now go to Canvas and let me show you where this is. You're gonna see this bad boy. So let me show you where this is. Go to Modules, go to Chapter 9, Sum Difference Proof. There it is. Look at that. That's just so beautiful. Looks like something you would find in a cave, drawn on the wall. And then something kills us, and we're the opening scene of a movie. So, all right. So let me stop sharing that, and I'll share it in a better way so I can write all over it. All right. So we're going to do some exceptionally weird shit tonight. Okay. And like I said earlier, how's that any different than regular nights? Let me set this up better. All right, let me put that by itself. All right, and where'd everybody go now? There you are. All right. So let's see. I want to make sure you guys understand what's happening here. So this triangle right here, this triangle right here, it's got an hypotenuse of 1. Is that cool? It's got a right angle right here. That's why this is the hypotenuse. The 1 is the hypotenuse, right? What angle is in it that we know? I got to make sure you can read what I've got down here. It's a little bit weird.
Is it beta?
Beta. I love it. So beta is this angle. Alpha is this angle. And then the big ass triangle has got alpha plus beta, which makes sense because it's both the alpha and the beta put together. All right. Not the alpha and the omega. I'm sorry. You don't want to mix those. Weird things happen. So let's first figure out, now see how there's another right triangle? There's actually 2 little right triangles. There's this right triangle, and then there's this bigger right triangle. Is everybody with me? And then there's even another right triangle. Holy shit. Okay. Now, I've got a kind of a final version of this. So if you just want to watch, I completely understand. If you want to try to capture everything that's happening, feel free. But I've got kind of like a final form of this, right? Golden worksheet. Like golden freeze. No? Okay. So first thing I want to do, this poor other little right triangle, can we figure out what his poor little hypotenuse is? Poor little dude. What the shit would this be? So it's in this big right triangle here. Is everybody with me? So what is this side related to? How's it with beta? What trig function would this side be related to?
Cosine.
Cosine, yeah. Cosine beta would equal this side divided by 1. Everybody with me? Isn't cosine beta defined to be this side divided by 1? So this side is cosine beta. Sweet. Okay, let me stop for a second. Do you start to understand that we're going to fill in like most of the lines in this thing? Do you understand what's going to happen? That's the plan. All right. Now, let's see. Where should I go next? There's a million different ways I can go. What's this here? What's this got to be then? Still working with the same triangle, so it should be really obvious what this is going to be.
Sine beta.
Sine beta, I love it. Okay, I like it, I like it. All right, now let's talk about this triangle here. Well, let's see. Let's talk about this big ass triangle. See, he's big this way, but then he stops here, right? Do you guys see what I'm saying? This triangle here. All right, so let me identify a few more right angles for us. That's obviously a right angle. That's got to be a right angle. Okay, so this triangle right here, this dude. What is this side? What's nice about this triangle? What's his hypotenuse?
1.
1. Again, so the side should be really simple, but what is his angle that I'm going to reference for these sides? What's the angle of the big ass rectangle? I mean, triangle. You failed trigonometry, Jeff. Damn.
Alpha plus beta.
Alpha plus beta. I love it. So this side is going to be a lot like this side. Obviously, is everybody with me? Because that's the x side. So that side, and let me be really specific here. This, because that's what I'm talking about. This kind of stonky little dude. Stonky? Stocks. I just put stocky and stonks. I made it stonky. This will be cosine alpha plus beta. Okay, so everybody with me? We actually haven't done much of anything at the moment. We sort of just verified some cosine and sine ratios. So obviously, what about this side here? And to make it a little bit easier, I'm going to put that out here. That's obviously got to be what? If this side is cosine alpha plus beta, this side is going to be
Sine.
sine. Let me see if I can do this. You ready? All right, this is going to be exceptionally weird. There we go. How'd they come out? Whoa, it's kind of big. Sorry. I should probably watch as I do it. I'm getting used to this thing. Hold on. All right, that's not too bad, Jeff. I can deal with that. Okay, so that side, and I just put it out here just because there's a lot of little sides in here we got to worry about. This is sine alpha plus beta. Okay. So let's see, what else can we get here? What about, let's see, which way do I want to go? What about this here? Let's see. Now look at this triangle down here. All right, let me remind myself of something. There's an intermediate slide that I have that makes this a little bit easier. Oh shit, did I just close it? Yeah, I did. I didn't mean to do that. Hold on, there's an intermediate slide. Okay, here we go. Kind of want to keep track of where I want to go next. Okay, I see where I want to go next. Not that, Jeff. Oh shit, what's the right thing? So many things open. Okay, here we go. All right, so what about this? So look at this triangle right here. This triangle, the short one, but the longer one. So this triangle, everybody with me? Let me know if you can't tell what triangle I'm talking about. So this triangle right here, what is this side of it?
Sine alpha.
Be careful, be really careful. The reason that these other ones are simple is because the hypotenuse was 1. This guy's hypotenuse is cosine beta. So what's sine alpha equal to? It's going to be this side divided by cosine beta. Is that cool? You guys with me? The reason these were so easy, this, and this, was because they were from triangles that had a hypotenuse of 1. So of course their sides are easy. This stupid triangle down here, poor little dude. I'm sorry, I didn't mean to call you stupid. It's not your fault. This guy's hypotenuse is not so pretty. So what is the side then here? It's going to be, multiply that up. It's going to be sine alpha cosine beta. All right, let's see if I can do this any better. I can do this, come on. Why did I do that? I don't know. Jeebus. All right, that's pretty gross, but oh well. Like I said, though, I have an intermediate slide that is typed. I think we might be, let me see, do I need anything else to transition to this other one? No, I think that, no, there's one more thing, of course. What about this side? So now that we know that this is sine alpha cosine beta, because it's sine times the hypotenuse. So this side is gonna, this whole side here is gonna have to be cosine of alpha times the hypotenuse. The same way. All right, are you guys appropriately freaked out yet? I have some of you guys completely stopped looking. I'm sorry. So what I like to remind you guys, and I might never have said this, and I haven't, if I haven't said this, I feel really bad. But here's something kind of cool. Whatever the hypotenuse is, let's say this is 35 degrees. Now just stay with me for a minute. Why did I make the triangle so tiny? I don't know. So leave me alone. Let me draw it again. This is kind of cool. This got me through a lot of my physics. And I wish I would have known to look at it this way when I was taking trigonometry. But this is such a cool idea. So say this is 35 degrees and say this is 7. This is not true, but it's good enough to work. This is so true about certain ways to remember things. I like to think of sine of an angle as the percentage of the hypotenuse that's in the y direction. So if I take 7 times the percent in the y direction, I end up with the amount in the y direction. And if I take 7, the hypotenuse, times the cosine of 35, that'd be 7 times the percentage in the x direction is the amount in the x direction. Isn't that basically what we just did? So I took the hypotenuse times the sine of the angle, that's the amount in the y direction. Cosine beta times the cosine of the angle is the amount in the x direction. And again, I sense that people have kind of tuned me out. That could be just in my own head. I'm fine with that. I just really try to follow along as best you can. Let me know if you have questions. Also to remind you, you are never going to have to do something like I'm doing right now on your own. This is explaining where certain relationships come from. And the book actually explains this in a completely different way that I hate, but I'm going to point it out to you in case you want to look at it, in case you like it better. All right. So I'm the teacher, though I get to decide how I teach it, but I will show you that the book shows it a different way. Okay. So let me transition to this other sheet because I think we're there. Yeah. So let me put this over here. So this is what I meant. This is what I promised. This is where we left off, correct? Just obviously written better. Oops, there's some answers at the bottom I don't want you to see yet. All right. So do you notice how I drew in an extra line here? Oh shit, and there's one other thing. Wait, don't look too much. There's one little thing I forgot. Dadgummit, Jeff. It's this tiny little thing, but it's necessary, it's important. I don't know if anybody noticed it, but can we figure out what that angle is right there?
Alpha,
How did you figure that out? Or did you just see it?
because the other side of the angle is the same degree as the alpha triangle.
All right, so right here, does anyone remember their geometry, what those angles are called? What letter does it look like on either side? So when I have two lines come together, doesn't it make sense that these angles and these angles are the same? Yes?
Yeah.
And they look like the letter V?
Yep.
So these are vertical angles. All right, does it matter? Does the name matter? No. What matters is you remember that they're equivalent, that they're congruent. Do you remember that word congruent from geometry? Ooh, baby. That brings back such a wide range of memories, I'm sure. Now stay with me now. What is this angle? All right, let's see. This angle is 90. This angle is alpha. What does this angle have to be?
90 minus alpha.
Yes, because altogether they have to make 180. 90 minus alpha plus 90 plus alpha is 180. Therefore, this angle is 90 minus alpha. And so in the same way, this angle must be alpha. Okay, all right. Does that bring back memories to anybody? Do you remember doing these problems where you had an angle way over here and you had to work it over here and you figure out what this angle way over here was? All right. Yes, I loved those problems. I would. So let's transition back to this better thing. Okay. So now, what can I do next? Well, let's see. Now that I've got this little triangle here set up, and let me show you, this is definitely a right angle here. What is this? To see if anybody kind of remembers what we just learned a minute ago. Let me do this and see, does that just freak people out? Yeah, let me not do that anymore. So here's the hypotenuse, correct? So how much is going to be in this direction? It's going to be what?
Cosine,
Yeah.
cosine alpha times sine beta.
So this is a beautiful thing to realize right now. Just like Rio said, cosine of alpha is the percent of the hypotenuse that's running in the x direction. Now, if you say that to a math professor, if you say that to me, I will correct you and say, no, cosine and sine are not percentages. So like I said, they're not a true percentage. It's a useful way to think of it. So cosine alpha is the percent of the hypotenuse that lies in the x direction. So cosine alpha times sine beta, that's what this is. Okay, let me see, can I do this? Is this, now screw it. Let me try that, I gotta get better at this. All right, here we go. Okay. Thankfully I have another, oh crappity doodah. Very thankfully I have another sheet after this. I think, do I? Oh shit, sorry everybody. I keep hitting the wrong button. All right, where was I? Here it is. I don't think I do. Well, that's too bad for everybody. All right, somehow we're gonna make it through this. I don't know how I wrote this so much better before. Oh well, too bad for everybody. All right, so what about this little piece here? Can somebody else tell me? God, I just can't let this go. I have to write this over again. So you guys think about that, this piece here. Why can't this work better? We could do this. All right, I just sort of lose track of how big it's supposed to be. Hello?
Is it sine alpha over sine beta? Okay.
But times sine beta.
Oh.
Now, we are ready. Believe it or not. I know it doesn't feel like we've arrived at a position, but we are now ready. Okay, watch this. This is kind of cool. All right, where'd you guys go? There you are. Sine alpha plus beta. Can you see the parts that it's equal to? Do you see how it's equal to this part right here? Plus what? So it's equal to sine alpha cosine beta. Plus what? What else finishes how long this is? Sine alpha cosine beta is a piece of it. What's the other piece of it?
Cosine alpha sine beta.
Cosine alpha sine beta. That is an identity. That is true. You pick any two angles you want to. This is true. Don't worry, I've got it written down here in better handwriting. It's like, well, not even handwriting. It's typed, it's written, so thank God. So do the same thing down here. Look, now this is going to be a little different. Cosine of alpha plus beta is not an addition, is it? It's this whole thing. It's this whole thing minus how much? Right? This is too much, isn't it? Cosine alpha, cosine beta is more than cosine alpha plus beta. So cosine alpha plus beta is cosine alpha, cosine beta minus
Sine alpha times sine beta.
sine alpha, sine beta. All right. So let me scroll down to where you can read things better. Oh, let me do this real quick. And then I'll everything will be written better. Don't worry. All right. But I have to make you suffer first. I'm a math teacher after all. So tell me this. Somebody tell me, what is sine of theta plus what symbol do I want to use for you guys? Sure, omega. What's sine of theta plus omega? Dadgummit, omega.
Isn't it just sine theta cosine? What is that? Omega
Trying to be.
plus cosine theta times sine omega.
All right. So I like the way you said that, but you need to realize people don't understand. There's nothing special about alpha and beta. Not a damn thing. They're just as not special as X and Y. The history of why we chose X to be the main thing is really interesting. And I have no time for that tonight. You should look into it. Why is X the thing? You should look into it. It's neat. So I just wanted to make that point. So what about this then? What is sine of theta plus theta? Somebody else. This is going to be too easy, hopefully. It's not 1. I don't know if you're raising your hand or saying 1. It's not 1. Somebody please. Sine theta plus omega is sine theta cosine omega, and cosine theta cosine omega. So what's sine theta plus theta? It's sine
Theta.
cosine
Theta.
theta plus cosine sine. So what's a better way to write this? Isn't this sine of twice theta? Didn't that come up earlier? Didn't I tell you we'd be doing this? See how Jeff holds to his word sometimes? Sometimes. Okay. And what's a better way to write sine theta cosine theta plus cosine theta? Say what? What's sine theta cosine theta plus cosine theta sine theta? What's a better way to write that? Come on, guys. Huh?
Right. Two
Yes.
sine.
2 sine thetas, cosine thetas, right? 2 sine theta, cosine thetas. Don't I have it? Two of them? That is what we call one of the double angle formulas. How could I develop the double angle formula for cosine? Can you come up with a way to figure out what cosine of 2 theta is? Maybe built on the way that I did it for sine. Couldn't I just take this and put what into it?
Two theta.
Yes, yes. Cosine of theta plus theta. So that would just be cosine theta minus sine theta, sine theta. What's a better way to write cosine theta, cosine theta?
Two cosine.
No, careful. No, we're not adding, we're multiplying.
Cosine squared theta.
Now, is there another way to write? Stay with me now. I just feel like I have about 4 of you still paying attention. I don't know. Remember, isn't cosine squared equal to 1 minus sine squared? Isn't that true? Cosine squared is 1 minus sine squared, yes? So could I write this as 1 minus sine squared, 1 minus 2 sine squared? Isn't sine squared equal to 1 minus cosine squared? So couldn't this be equal to 2 cosine squared minus 1? All right, so let me show you this written better. I'm going to post this up there too, don't worry. But here's all of it written better. So there's the main thing we proved directly from this. Here are the double angle formulas we just proved. And here is what to do to figure out the difference formula. I know what sine of alpha plus beta is, but what sine of alpha minus beta? All right. How is this? All right, let me talk about how this is useful, because it's always an immediately good question. Okay, Jeff, that was a fun trip down freaky ass math lane. What the shit does this do for me? Right? That's an excellent question. Kind of worded less than respectfully, but I recall that was me talking to me, so that's fine. So watch this. Can we currently, before today, were you able to tell me an exact answer to what sine of 15 degrees is? No.
No, not really.
So, but is 15 degrees the difference between two angles that we know sine and cosine of? Give me two angles we know. Or give me several angles that we know the trig functions for, trig values for. 0,
45 and 30.
45, 30. There you go. 45 minus 30. We could have used 60 minus 45, right? But 45 minus 30 is beautiful. So from this rule, what is sine of 45 degrees minus 30 degrees? Here, you guys do it. I'm tired. So here is what sine of alpha minus beta is. Alpha, 45, beta, 30. Please figure out what this is. Give me an exact answer. Can't make me do it, Jeff. No, I can't. You're right. You could sit there and draw a duck. But you're going to have to do this as simple. Might as well do it right now when it doesn't count for anything.
.26.
Wait, no, that doesn't sound like an exact answer anyway, so don't give me that. I want the exact answer. And don't say anything yet. Let me give myself some more room here. All right. So let's see. What would this equal? Sine of so I know in general, sine of one angle minus another is sine of the first cosine of the second minus sine of the second cosine of the first. That's the formula. Why is that true, Jeff? Because of all the shit we did up here, right? We proved it. Even if you didn't understand the steps, all the steps were understandable. So you know it came from well-established rules. And this is about the time I want to remind you guys that all that sine and cosine and tangent and all that stuff means is ratios of sides of right triangles. And look at all this shit that we've done with it. It's crazy. So what's this gonna be? Sine what, cosine what? What goes here? Sine.
$45.
45 cosine 30 minus sine
30,
30 cosine.
45.
So I want you to notice something. All right, now listen, guys. Well, let me see. Let's finish this, and then I want to point out to you. I'm going to prove to you in a minute, and this is going to help us through a lot of trigonometry. Cosine is an asshole. Cosine is an asshole. Cosine is an asshole. If you remember what I just said, it will help you with so many identities and ideas. I will show it. I'll show you, and I will point it out every time we have another situation where cosine is being an asshole. I will point it out to you. It even carries over into calculus. And there are certain teachers that kind of have bought into my philosophy of cosine being an asshole. So what is sine of 45? That's a beautiful angle, right? What's sine of 45?
Square root 2/2.
That's right, random British lady. What about cosine of 30? Somebody else tell me that.
1/2.
No. Cosine legs the x-axis. 30 degrees is closer to the x-axis, so cosine will be bigger. So
Rad 3/2.
Rad 3/2. Sine of 30 is the opposite situation, so that's going to be what?
It's 1/2.
Good, because sine likes the y-axis. 30 is far away. Sine gets scared. It's just 1/2. And of course, cosine 45 is root 2/2. So what do I end up with? What do I get here?
That 5,
No.
6,
Rad 6 over
4.
4 minus
Rad 2/4.
Now, can you simplify that anymore?
No.
Of course not. I love it. Done. That is what's called an exact answer. The minute you write any decimal, you are wrong.
Could we not put it over 4?
Of course you could. So you could put square root of 6 minus square root of 2/4. Sure.
Okay.
All right, so here is why cosine is an asshole. I want to point this out. And this doesn't only happen here, or else I would not have made this a big deal. Do you see how sine sees alpha plus beta? So it says, okay, here, let's take turns, cosine. I'll do alpha, you do beta. I'll keep the plus a plus, and then I'll do beta, you do alpha. Okay, cosine? Cosine sees alpha plus beta and goes, me first, screw you. Cosine. Plus, that's nice. I'm going to make it a minus. Okay, now you bring up the rear of the sign. So, I mean, that's, again, I have no idea if this is going to help anybody. That definitely helped me remember these identities because I had the hardest trouble memorizing this shit when I was in trigonometry. And then later I figured cosine's an asshole. And then I realized, holy shit, this works almost everywhere. Cosine's an asshole. Anyway, all right. I don't know if this is going to help. So down here, you can see the opposite happening with here, right? The minus is still a minus. Sine and cosine still taking turns. The minus becomes a plus when it's cosine because he's an asshole. And cosine first. All right, maybe. Look up here. Look at the sine of the double angle. How many options are there? 1. Sine says, oh, I know you have a lot of shit to remember. Here's 1 option. What about cosine of a double angle? Here's 3 things it could be. Have fun. So depending on the situation, there might be just one of these that works depending on the situation. So you have to kind of figure out which one is going to work in this situation. Sometimes it doesn't matter, but a lot of times it matters which one you pick. All 3 of those are equally true. They're not all equally useful in all situations. Does that make sense? Okay, maybe. If it doesn't make the most sense yet, it will make very much sense very soon. All right. You shall see. Okay. All right. I have no idea how you guys felt about this. Now, again, let me show you what the book does for this. Where'd you go, book? Just to give you an alternate perspective. And then I think I'm going to let us out of here because this is plenty. What do you guys think? Oh, wait, somebody chatted at me. Let me see what that says. Yeah, if I ever ask you to prove one of the formulas, it would most likely be a bonus situation. I might ask you to prove like sine squared plus cosine squared is 1, given a certain setup, but I mean, that should be something you could handle. But I'm not going to ask you to prove sum or difference formula unless it's like a bonus problem. Right? And even then, there's no way in hell I'm going to give you that. Can you imagine that? You have so much time left over, you can redo everything we just did with that? No. All right, let me show you this. So here's what the book does. The book does something that just bores the shit out of me. So it sets it up in the unit circle. Do you see that? Alpha, beta, and they actually do this difference formula first. This is just disgusting to me. So they set up all these distance formulas. See how the distance to these points? I mean, I'm already just tired. But I don't know, maybe somebody out there likes this approach better. So if you hated my approach and you want a different proof of the sum and difference formulas, take a look at the book. They give you a whole different, they don't use triangles really at all. They sort of do, of course, but they use the unit circle with endpoints, distance formulas, and they end up with the same identities, which is kind of neat in its own right. I just think the other way, the way that I showed you, obviously I like it better because that's the way I showed you.
It was slightly less confusing looking at very least.
Yeah, I mean, this is a lot to take in, and it's not as immediately clear what the visual is supposed to mean. Yeah, I agree with you. But this does have some advantages. It is a little more cleaner from the beginning. There's not as much ambiguity with some of it. Anyway, so, you know, give and take. Let me just see. What was I going to say otherwise? I think that was, there was one other thing I wanted to say and it's gone. Okay. All right. Yeah. Oh, let me do this. So I'm going to unlock this. Let me show you, and then I'm going to let you guys go. I'm going to unlock this right now. And a half. Well, somebody left. They couldn't wait. All right. Fine. They're like, I'm going to look at it later. This bad boy, right? Trig laws, which to memorize. Does that sound intriguing? So this is kind of, I don't mind unlocking this now, even though we haven't talked about some of the stuff on here. Some of this looks very familiar. There's the reciprocal identities. There's the sum and difference we just did, right? Pythagorean identities. This is in our future. This is in our future. Right? So don't worry, but do you see how, look at this last one. What does that look like? The first part.
Pythagorean.
With extra shit, right? So this is like Pythagorean in a non-right triangle. Yeah, baby. So we're going to prove this and I'll show you what the hell that means. These should look familiar if you've been reading the book. Here's some neat stuff about inverse sine and stuff, right? The domain is, do you guys remember this here? So I got it all nice and compact for you. And then something else, and here's the even and odd identities, right? All in one place for you. Here's the double angle identities we just did, right? Right? And then here's something else that we haven't talked about, but it's just like one step away here. So we're going to talk about that next time. Everything above this black line, you must memorize. Every calculus teacher will expect you to know all of these things when you enter calculus. Do you understand? If you go to calculus after passing my class and you don't know something up here, you... All right. So you must memorize all this. Anything down here, I will not make you memorize. One big reason is because I have never memorized these either, because I didn't see a need to. Another big reason is, as a department, we decided these were unnecessary for students to memorize. So that's kind of nice. That jived up pretty well. Is everybody with me? Does everybody know how to read this thing now? Everything up here you have to memorize. But you can have this sitting next to you as you do homework. Cool. All right, no worries. All right, everybody. That's enough. Let me know if you need to hang out. Otherwise, you're free to go. Thank you for putting up with me. And
Anytime, Professor.
you're like, I got to, man. We're not done with the class yet. All right.
See you next time.
All right, guys. See you.
Thank you.
Sure. Is everybody all right? I'm gonna head out. Isabel, you're good? What's up?
So for this summer, what classes were you teaching again?
Summer, I'm just teaching 160.
Oh, okay.
Yeah. Yeah, because Rio was asking me about the 180s. Currently the 180, is that what you're taking next?
Yeah.
Okay. Currently the 180s at Grossmont are supposed to be online, but I don't know if you were here earlier when I said that that's back up in the air.
Oh, okay.
It might not be, but I can't say one way or the other right now. So Rio was worried because he didn't really want to take an on-campus class yet. So he was looking at Cuimaca, but now Grossmont's might be on campus. And both of the people, I can't remember who's teaching that now. I think it's Green. Let me see. Anyway, I don't know. If you have questions about the teachers, I can tell you who I recommend.
Okay.
Yeah.
Sounds good. Thank you.
See you. All right. Charles Macy, you guys good? Oh, Charles.
Yeah, just a quick question. And so that's what we just went over with the 15 degrees, right? It worked out pretty good because we use 45 and 30.
Yes. So obviously, there's still an infinite number of angles we can't do by hand. Yes?
Okay, yeah, that's what I was gonna ask.
That's a perfect thing. So we're going to learn the half angle formula.
Okay,
So we'll be able to do like sine of 22.5 degrees because that's half of 45 degrees. Are you with me?
yes.
All right. Now, that is the immediate use of those. That is definitely not the only and not even the most often, the most applied use. Are you kind of with me? So
Yeah.
I agree with you. Your tone is exactly right. This seems barely useful, Jeff, right? We were able to do like 2 more angles. Good job. That's the immediate thing. And it's not even the most impressive use of it. So there's more you can do with it. That's just like, all right, we know this. Here's what we can do right now. We can do this weird shit. Yay.
Yeah.
So I appreciate you got the exact right attitude.
Well, no,
Yeah.
I don't like going into homework and then being like, all right, this is what we're supposed to do, and this is not what we went over.
Oh, I see what you mean. Yeah, they're not going to suddenly ask you to do the sine of 3 degrees or something. Don't worry.
Okay.
It's going to have to
Alright,
be
well,
some very set numbers, obviously, right? Yeah. But what's more important is using it in trig identity stuff. Yeah. And that's what
Alrighty.
lead into calculus. Calculus relies on us rewriting trig expressions to make the calculus stuff easier to do. So that's kind of like where they really become useful is when I rearrange things and use trig identities. Then when we attack it with the calculus stuff, it works so much easier if we rewrite it in a different way.
Oh, okay.
So that's where the real usefulness comes in. Yeah. But you're right. I sort of oversold it a bit with, with that, but I just wanted people to buy into it for now.
Oh, well, it was good. The other question I had is so I don't think I'm gonna take a summer course because my baby's coming right in May.
Yes.
So do you have like a textbook that, because I took your class originally first and then I dropped out last semester, and so this is like my second time taking this course, but I basically worked through one of these calculus teach yourself books.
Yes.
Well, for your next class, do you have a book that would help prime me up for calculus by the time I'm ready to take it?
Well, I mean,
Fall.
I'll tell you, I'm considering using the, you know how I use the OpenStax book for pre-calc? There's an OpenStax book for calc.
Okay.
So if you go to the OpenStax, and I'm thinking about using that book, I got a couple of other open resource books that I have to look at to see if another one's better. but I kind of like the idea of this website and stuff. But anyway, let me see, where is it? Is it still up here? Yeah, there it is. So like Calculus Volume 1 on the OpenStax website. Even if I don't end up using it, like you said, it's just a kind of a review book. It's a place you can go to review exercises and try some stuff out. It's got answers for the odd problems, right? I mean, but the other thing you can do is just type in online calculus. Let's see, I haven't done this in a while because I have online calculus textbook. And there you go. MIT is really good for this. MIT OpenCourseWare. They have a whole calculus course that's up on it. So you can basically take an MIT course online. Dude. So they have, yeah. So here, let me put it in the chat. MIT, I've looked at a few MIT courses before. They do a really good job of putting their stuff up online. So there's the one. Oh shit, I sent it to the wrong person. There.
Awesome.
I mean, you know, but that's only 2 of 800,000. So,
Oh.
So if you search
Alright.
for open source calculus or online free calculus textbook or something, I mean, you'll get all kinds of hits nowadays.
Yeah, I didn't want to let it kind of get stale and stagnant.
Yeah, understood. That's a good one to go in with a head start. Yeah.
Bye.
See you later.